Okay. Now suppose you have switched on your AC. In which direction heat flows?
Outside.
From room
Inside
to
to
outside.
outside.
From room to outside.
Room to outside means lower to higher or higher to lower?
Lower to higher.
Lower to higher.
Does it contradict this statement?
No.
Why?
No, sir.
External
Because
agency.
AC is a external agency. AC is doing
Yes.
some work, sir.
That means by spontaneous way the heat will flow from high to low temperature. But lower to higher possible, you have to use some external agency. That is the machine. Did you understand? All of us know water flows down the hill, isn't it? Water flows down the hill. Is that right?
Yes, sir.
But if
Yes,
we use
sir.
pump,
Upward.
it can go upward, right?
Yes,
But
sir.
which is spontaneous?
Down
It
the hill.
flows
Water
down
hill.
the hill. Okay. So that is the statement. By spontaneous manner, it will flow from higher to lower temperature, but reverse may be possible, but you have to do some external work. This is the statement. Next. Another statement is there that was given by Planck Kelvin. That is known as Planck Kelvin statement. What is that? Heat cannot be converted into work. Completely. In a cyclic process. Heat cannot be converted into work completely in a cyclic process. Heat cannot be converted into work completely in a cyclic process. Before we explain it, we should define few parameters. What is that? What is meant by heat engine? What is this? It is a device which can convert heat into work. That means if you want to convert heat into work, first thing is that you have to supply heat, isn't it? Am I audible?
Yes,
Yes,
sir.
sir.
Yes, sir.
So you have to supply heat. Which can supply heat is called source. What is source? It is the heat reservoir. It is the heat reservoir which can sorry. It is the heat reservoir which can supply heat without change in its temperature. Similarly, something is there which can absorb heat, that is called sink. The heat reservoir which can absorb heat without change in its temperature. Source means it can supply heat. That's why it will have the temperature higher than the sink. As per the Planck, no heat engine can convert completely heat into work. Since it cannot convert it completely, we used to define efficiency. What is that? Fraction of heat converted into work. If we supply Q amount of heat, thereby we get W amount of work. Their efficiency is symbolized as eta. Eta is equal to W by cube. As per second law, eta is not equal to 1 and it always less than 1. What is the justification of this? To justify it, Carnot proposed a cyclic process that consisting of 4 steps is known as Carnot cycle. How many steps are there? There are 4 steps. And to get maximum work, the proposed steps was all reversible. So I'll tell you in detail Before that, let us write what are the steps. It was having the 4 steps as I told. Reversible expansion. Second was adiabatic reversible expansion. Third was to return to go back. Third one was isothermal reversible compression. We were trying to return. And fourth one was adiabatic reversible expansion.
compression হবে না
Oh, sorry, compression. So there are the 2 steps of expansion and followed by 2 step compression. One isothermal adiabatic, but everyone is reversible. Carnot proposed this cyclic process for Carnot's engine. Carnot's engine was allowed to undergo these 4 set of steps. What is that? Carnot's engine is nothing but 1 mole ideal gas. Confined in a cylinder fitted with weightless and frictionless piston. Which works between source, which is at temperature T1, and sink, which is at temperature T2. Let us see what is there. So let us assume we have taken 1 mole ideal gas at pressure P1 and volume V1, and slowly it is being expanded. Slowly means to make the process reversible, and when it will expand, it will have to do work, and when it will try to do some work, its energy should decrease. To avoid it, let us place it near to the source. What I'm telling, we have 1 mole ideal gas at pressure P1, its volume is V1. It is being allowed to expand reversibly. When it will expand reversibly, it will perform some work. Its energy may decrease. That's why we thought that let us place it over to the source. And whatever the decrease in energy expected, that energy will be supplied to the source. And that process was continued until its pressure reduced to V2 and volume reduced to V2. And since it is placed near to the source, the temperature was kept constant. So it is the isothermal process. And during that process, it takes some amount of heat from the source. How much? Say Q1. Did you understand what I told?
Yes, sir.
Yes, sir.
After that, we have stopped the heat supply. Then again, it is allowed to expand. First step was expansion, but isothermal. Next, we have stopped the supply of any heat. Again, it is being allowed to expand reversibly. But since we are not supplying any heat to it, when it will expand, its temperature will decrease to T2. Would you understand? And
Yes, sir.
we are not supplying any heat, that means the process will be adiabatic. And it is also expansion. After that, let us try to go back to the initial stage to make the process cyclic. After that, let us try to go back to the initial stage to make the process cyclic. Now, it may happen that directly we could not be able to go back to the initial state. You may have to choose certain intermediate state. That's why from the state P3, V3, T2, let us try to compress the gas. So it is a compression. But when we are trying to compress the gas, start to rise due to enhanced energy, but that energy will be released by it is absorbed by the sink. So at this stage 3, it is placed near to the sink. Whatever the energy enhanced, that will be absorbed by it to keep its temperature constant. So the third step is isothermal reversible compression.
Sir,
After
repeat
that,
again. Sir, could you please repeat this?
yes, we from P3, V3, T2, right?
Yes, sir. Yes.
Or from beginning?
So P3 with P2, P3, 2.
Okay. Now through expansion, we reached at state P3, V3, T2. Now we thought that we have to go back to the previous stage, means P1, V1, and T1. That's why we started to compress the gas, because through expansion we came over here. Let us try to compress it. And when you will try to compress it, work will be done upon it. So its energy may increase. And whatever the energy increase, if we place this system towards the sink, the excess energy will be absorbed by it, such that you can keep the temperature constant to make the process isothermal. Did you understand?
Yes, sir. Okay, sir.
Okay.
Yes, sir.
After that step, again we are trying to compress it to get back to the first state, that is the P1, V1, T1. But since gas is being compressed, its energy may increase, and that's why T2 increase to T1, such that we can go back to the P1, V1, T1. These are the four steps which was proposed by the French engineer Carnot, and it is known as Carnot cycle. It is the imaginary cycle by which we will try to calculate how much amount of maximum work we can get from here. But remember it, the step 3 is the adiabatic compression. Sorry, state 1 is isothermal expansion, state 2 adiabatic expansion, state 3 isothermal compression, step 4 adiabatic compression. These are the four steps which was proposed by Carnot, and remember that every steps here is reversible. Now we'll try to calculate how much work will be done by these steps. Have you drawn this cycle?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay. I have to shift to the next page, but just before that, throughout the four steps, we'll try to apply this relation dq equal to du plus w, which we got from the first law.
First,
Now dq means energy supplied. How much energy supplied in the state 1? Q1.
Sir, Q1.
How much du is there? Temperature remain constant. How much du is there?
sir.
0.
Zero.
Because it is isothermal process, right?
Yes, sir.
Yes, sir. 0.
Then q1 equal to w. Say for step
Yes, sir.
1, step 1, let us write the work equal to w1. For step 2, it is w2. For step 3, it is w3, and for step 4, it is w4. Is it clear to all?
Yes, sir.
Yes.
Yes, sir.
We are interested to calculate the total work. How can it be possible? We will calculate w1, we will calculate w2, we will calculate w3, we will calculate w4, then we will add it, then we will get the total work, right?
Yes, sir.
Okay.
Yes, sir.
Step 1. As we told, dq equal to du plus w. dq equal to du plus w. How much dq is there? dq is there equal to q1. Du you told 0.
0.
W means what? W1, right?
Yes, sir.
Yes, sir.
Now what type of work that is? Reversible work, isothermal work, right? And
Yes, sir.
you try to remember isothermal reversible work for 1 mole ideal gas. We had the formula RT ln V2 by V1. Can you remember it?
Yes, sir. Yes, sir.
Yes, sir.
Then can we then write W1 equal to temperature is here T1 ln V2 by V1?
Yes, sir.
Okay. So all of you know W1 equal to
Can you please
RT1.
repeat once again?
When we discuss about the reversible and irreversible process, there we got this relation. Reversible work was equal to RT ln V2 by V1. When gas was expanded V1 to V2 at temperature T constant by 1 mole ideal gas. Can you remember it?
Yes, sir.
And here
Yes,
the
sir.
T means what? In our present scenario, T there T1, and volume of the gas was changed to V1 to V2. So W1, that is the work performed in the step 1, equal to RT1 ln V2 by V1. Did you understand?
Yes, sir.
Okay.
Yes, sir.
Now what is the second step? What is the second step? Adiabatic process, right?
Yes, sir.
Adiabatic means dq there 0
Yes, sir.
and w, let us write that w2, and all of us know du equal to cvdt where temperature is changed from T1 to T2. Can we write it?
Yes, sir.
On integration, we will get the total work. That means W2 equal to, we are getting minus CVDT T1 to T2. Isn't it?
Yes, sir.
Now, W3, what is the process?
Sir,
That is
previous
also,
slide one, sir. Please.
Isothermal compression.
yes.
Thank you, sir. Done, sir.
Okay. That's step 3. That was the reversible compression of 1 mole ideal gas. Same formula, RT2 ln probably V4 by V3. Am I right?
Yes, sir. Yes, sir. V3, V4 by V3.
Yes, sir.
Let us write this is equal to W3. Last step is the step 4.
Adiabatic.
Step 4, so W4. As usual, that was T1 to T2, it will be T2 to T1. Reverse process of CVDT. Third is the reverse to first. Fourth is the reverse to second. Isn't it?
Yes, sir.
Third is the reverse of the first. Fourth is the reverse of second.
Yes, sir.
Yes, sir.
So we got W3, W4, and in the previous one W1 and W2, right?
Yes, sir.
Then what to do? You want to get the total work during the cycle.
We add
So
all the
W
work.
cycle. W cycle equal to what? W1 plus W2 plus W3 plus W4. You tell me in the first one, probably it was the RT1 ln V2 by V1, right?
Yes, sir.
Then T1 to T2 CVDT, right? Plus RT2 ln V4 by V3 minus T2 to T1 CVDT.
W to W4 तो cancel हो जाएगा.
But by expression we have to write first, then later on then we will cancel, isn't it? I have used all this term, but W2 get cancelled by W4, isn't it?
Yes, sir.
Yes, sir.
Then what we have then? It is RT1 ln V2 by V1 plus RT ln V4 by V3.
Sir, T2. Sir, in the second part,
T2.
RT2.
It is T2. This one, na?
Yes, sir.
Okay. Now let us go back to this slide. Now this step was adiabatic expansion of ideal gas, yes or no? And reversible.
Yes, sir.
And this is the reversible adiabatic expansion, compression of ideal gas.
Yes, sir.
Yes,
In
sir.
in adiabatic process, try to remember that we derived a relation in the previous class, T v to the power gamma minus 1 equal to constant. Can you remember it?
Yes, sir.
Yes, sir.
Then for the step 2, can we write T1 into V2 to the power gamma minus 1 equal to T2 into V3 to the power gamma minus 1, because T v to the power gamma minus 1 equal to constant.
Yes, sir.
So what I'm telling,
Repeat again.
for adiabatic reversible expansion or compression of one mole ideal gas, in our previous class we derived this relation Tv gamma minus 1 equal to constant. Can you remember it?
Yes, sir.
And if it's so, then T1 into V2 to the power gamma minus 1 equal to T2 into V3 to the power gamma minus 1, because T1 V gamma to the power 1 equal to constant.
Yes, sir.
Similarly, T2 into V4 to the power gamma minus 1 equal to T1 into V1 to the power gamma minus 1,
Yes, sir.
because these steps was adiabatic and this is the adiabatic process. Is it clear to all?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
In the next page, you will help me. In your copy, first you write T1 into V2 to the power gamma minus 1, T1 into V2 to the power gamma minus 1 equal to T2 into V3 to the power gamma minus 1. Did you write? And another one you write
Yes, sir.
T1, another one you write T1 into V1 to the power gamma minus 1 equal to T2 into V4 to the power gamma minus 1. Did you write?
Yes, sir.
Yes, sir.
Please,
V2 by V1, V3 by V4.
please help me. T1 into V1 to the power gamma minus 1, did you write? Equal to
Yes,
what you
sir.
wrote?
Sir, sir.
T2 into V.
This,
T1 into V2.
V2 V4 gamma minus 1. So T2 into V4 to the power gamma minus 1.
T2 into V4 gamma minus 1 and T1 V2 to the power gamma minus 1 equal to
T2, V3,
Gamma minus 1.
T2
T3
V3.
V3, gamma minus 1.
T2.
Am I right?
Yes, sir.
Then can we write this by this equal to this by this? Can we write it?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
Then T1 T2 got cancelled.
Yes, sir.
Yes, sir.
Then can we write V1 by V2 equal to V4 by V3? This T1 got cancelled. T2 got cancelled. Gamma minus 1, gamma minus 1, gamma minus 1, gamma minus 1, all cancelled. Then we have only what? V1 by V2 equal to V4 by V3.
Yes, sir.
Isn't it?
Yes, sir.
Then V4 by V3 can be replaced by V1 by V2, yes or no?
Yes, sir.
So let us replace this V4 by V3 as V1 by V2. Could you hear me?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay. Thus, we have or RT1 ln V2 by V1 minus RT2
ln V2
ln
by
V2
V1.
by, isn't it?
Yes, sir.
Thus T1 minus T2 R ln V2 by V1. Can you write it?
Yes, sir.
So this is the total amount of work what we can get.
Yes, sir.
How much heat you supplied? Q1.
Sir, Q1.
And you see there it was equal to RT1 ln V2 by V1. Isn't it?
Yes, sir.
Then what is about the efficiency? Eta equal to then W cycle by Q1, yes or no?
Q1.
T1
Yes,
minus
yes.
T2 upon T1.
Then is it coming T1 minus T2 by T1?
Yes, sir.
So this R ln V2 by V1, R ln V2 by V1 got cancelled. This T1 minus T2 by T1, right? So ultimately we are getting eta equal to 1 minus
T2 by
T2
T1.
by T1. Isn't it?
Yes,
Yes,
sir.
sir.
Yes, sir.
Now if we choose T2 equal to 0 Kelvin, what is about eta? It is 0 Kelvin,
Eta
not
equal to
okay.
1.
Eta equal to 1. Does it contradict Planck Kelvin statement? Planck told that eta not equal to 1, but if we put T2 equal to 0, it is coming as 1.
Yes, sir.
That means what?
Yes, sir.
Heat can be
It
converted into
contains.
work completely.
Yes, sir.
Does it contradict Planck Kelvin
Yes,
statement?
sir.
Yes, sir.
Sure. So as for this calculation, eta equal to 1 means it contradicts Planck Kelvin statement. Then you tell me, can you generate 0 Kelvin temperature?
No, sir.
No, sir.
That means
No,
what?
sir.
That means what? T2 is always greater than 0.
Yes,
Yes.
sir.
Yes, sir.
Yes, sir.
That means what? Eta is not equal to 1.
Yes, sir.
Yes.
Yes, sir.
That means eta always less than 1.
Yes, sir.
So it supports the Planck Kelvin statement, right?
Yes, sir.
Yes, sir.
Not only that, if we create more difference between T1 and T2, more efficiency will be there. Did you understand that?
Yes.
Yes, sir.
So we want to choose T2 low as far as possible to make the machine more efficient,
And to one higher.
and T1 higher. Is it clear to all?
Yes, sir.
Can you please repeat once again?
Mathematically, if we put T2 equal to 0, then eta is coming as 1, right? If eta
Yes,
is
sir.
1, it looks that efficiency may be 100%.
Yes.
But in practical
possible.
scenario, can we create 0 Kelvin?
No, sir.
That means your temperature is always more than 0.
Yes.
If it is more than 0, then always it will be less than 1.
Yes, sir.
So less than 1 means what? Your efficiency is not 100%.
Yes.
So you'll have so always less efficiency than 1, isn't it? It means
Yes.
that entire heat cannot be converted into work. It means
Okay.
that entire heat cannot be converted into work. Could you understand?
Yes, sir.
Yes,
If
sir.
it's so, we have some inefficiency.
Yes, sir.
Did you understand? We have some inefficiency,
Yes, sir.
which is measured by the function is called entropy. Inefficiency is there, which can be measured by the function is called what? Entropy. Would you understand?
Yes, sir.
We will start it in the next class. We will
Sir,
start it
efficiency
in
can be
hello.
negative.
Right.